Hi, thanks. So hi everyone, I'm really happy to be here and give this talk. So just a quick intro. So as Lauren said, my name is Moran. I'm machine learning manager at Booking. I'm also a PhD student in information system engineering, researching NLP aspects in temporal graphs. Previously, I worked mainly on the machine learning domain in the diagnostic robotics, like a healthcare domain, and I really love traveling, so Booking is really exciting domain for me. And in today's session, we are going to speak about text to topic, which is a model that we've developed in the team to identify topics within text, and we will go over all of the things that we have done. So let's start with a quick motivation. So let's say we have this James family that are dreaming about their next holiday, and we really want to fit their next holiday to their needs. And they scan hotel pages and trying to find the best property relevant for their needs based on reviews and more relevant data. So let's say they have some like must-have things that they want. They want the property to be kid-friendly, with beach, themed parks, swimming pool, and also more like snorkeling, spa, or shuttle, more like nice to have stuff. So we would like to find the best properties and help them to find properties that match best their needs. So how can we do that? And how can we help not just the James family, but also like over 100 million users that we have in Booking to find their needs, and this is where we came with this model into the picture. So we have a lot of user reviews, and we can leverage them in order to find the needs and in order to use it for different use cases that I will elaborate next. So how many reviews do you think we have in Booking? So we have many reviews. We have like 28 millions of properties like hotels, homes, apartment. And taking all of these properties, we have 240 millions of reviews from the last 3 years with a lot of languages, multiple languages. And we need to be able to process all of this, right? Like all these reviews, all these languages, and from different properties. So the idea is that we have a lot of text within Booking.com. So we have also the search queries and question and answering questions inside the property page. We have the reviews, we have forums. And given all of this, we want to extract the topic and to find beach, spa, family-friendly, safe area topics, for example. Then if we found properties that mention these topics for the James family were interested at, like the beach, the kid-friendly topics, and we find properties that highly mention these topics in a positive manner, so we would like to surface this property for the James family, for example. So we have many applications to do that. So we have themes recommendation, destination recommendation. We also use this model, the topic one, to find fraud messages and fraud properties, and to do some automatic messaging. So let's see a really simple example. So let's say we have this review, the bed and pillows were not comfortable, the room was small and very cold at night, not at all what we expected. So we would like to find all of these topics, like also the sentiment. So we know the review is negative, and also we know we have these topics in this review with these probabilities. And once we have this kind of structured data per review, we can aggregate it to the property level and to find what are the main topics that this property is good at, right? and then like to best personalize the experience each user has. So we are using, to build this model, we are using many data sources. One of them is, of course, the reviews. So we have a lot of reviews, as I mentioned, but also we have questions and answers, like in the property page, people can ask, how can I do early check-in? How can I take the taxi? So we can even use this information and the topics that are mentioned there to better understand the property. We have also search queries. So if you are going to search even in Google and even in like inside Booking, so we can understand your intent, right? So if you will write romantic hotels in Paris, we know that a romantic topic is very relevant for you. Then we can surface properties that are relevant for romantic. So we also can extract topics from the user query. And we have many communities at Booking. So one of them is travel community, where people can discuss about some destinations. Also, we have partner community, where users can discuss about partner issues that they have in Booking. And we also use this information and this data set to train the model. So now that we know the topics from the data set, what we can do with them. So as I mentioned, we can do a lot of stuff. So let's go over some use cases. So first, we can, for example, recommend on destinations. So if we know this, for example, this carousel is about city recommendations. So we can identify the top destination for city using the destination reviews that we have that mention city as a major topic in the reviews, or beach or romance, for example. Same we can do to supply the topics here in this carousel, so we can see what are this destination is good about. It's good on relaxation, surfing, diving, snorkeling, and this we can do also with the topic detection. We know which topics are the main one that highly we see that we have a lot of mentions of these topics, and also like in a positive sentiment. Another example is to also highlight the top facilities of a property. So we know from reviews and the question answering what are the top properties, what are the top topics mentioned in this property, and then we can put a ranking list of the facilities that are very relevant for this property. Again, we can do it personalized. If we know there are some facilities that are more relevant for families, we can choose them. Another completely different use case is also to find fraud properties. So we see that guests are mentioning in the reviews things that can help us to identify fraud properties. Like actually mention this is a fraud property, or like to mention that the partner asked to give the phone number or the bank account details and things like that. Also, we use this topic detection model to do a messaging, automatic messaging with templates. So if, for example, we got our customer service got a message from a partner, I can change my cancellation and my free cancellation. So identify this topic is on cancellation, and then we can transfer this message into the relevant people inside Booking. So we use it to orchestrate all the messages that come into Booking and to direct them to the right place. Yeah, so we are using a lot of data sources, and we saw in the model that we will see in a second how it can help to learn other domains, and we build general capability that can cover a large variety of use cases and not just one. So we have one model that can serve a lot of use cases, and we build this product with customer in mind and guests and partners. And also we define the topics after a lot of iterations with stakeholders and customers in Booking. So let's go over to the modeling part itself. So after we saw all of these needs, we need to build a model that is able to detect topics accurately. And we don't want to define a set of lexicon per topic. We just want to identify a topic without setting a predefined lexicon. We want this model to allow zero shot, because, for example, tomorrow morning, another person from another department in Booking wants another topic about jungles, and we want the model to be relevant and return predictions for these topics as well. So we want to be able to support zero-shot predictions. We want to fine-tune the model to the tourism domain and to the relevant topics we have in the tourism domain, and we want to support multiple language. So I will go over the model architecture that we built, how we collected the data, how we evaluate and did experimentations, and the zero-shot and some demo. So let's go over some architectures that we have. One is the course encoder. The idea behind the course encoder is that we have one BERT layer that gets the two sentences. We have a classification head, and then we get a probability that the sentence one is similar to sentence two. So why it's a course encoder? Because we insert to one BERT layer across input of the two sentences. So in our case, it's not two sentences, it's actually the text and the topic. So we have the text, for example, best private pool in the room was good and nice, room was good and nice breakfast, and we have the topic, and we want to concatenate them before the BERT layer as one input. So we have the first text, we have a separator between them, and then the topic tokens. Then we insert this input into a BERT layer, and then we get a CLS token that represents the embedding of the two inputs, both text and the topic. Then we can predict using this embedding if the text and topic are related, 0 or 1. That's how when we have, for example, a new topic that the model didn't train on, so we can do the same, like take the text and the topic tokens, the new topic tokens, and get probability that the topic is mentioned in the text. Another option is the biencoder, which is to do this exact, mainly the same, but with two heads. Like we have head of BERT layer for the first input for the text, and the second one for the topic. So we have two BERT layers that are not shared, are not crossed, and we have a biencoder for each one of them. So in our case, we have the text, so we embed the text part, we embed separately the topic part, we get an embedding from the CLS for each one of them. Then we can multiply them to get a prediction, for example. So this is the idea. So here with the biencoder, we use cosine similarity, so we get the two embeddings for each part. We normalize them, and we calculate. So we calculate basically the cosine similarity between these embeddings. And then we can use a binary cross entropy on top of this cosine. So actually, we tried multiple architectures. So we used the cosine also with the CLS, and not just the CLS. CLS is the beginning token of the sentence, so that represents the whole sentence. But we used also min pooling, taking the tokens inside the topic and inside the text separately, and min pooling them. Also max pooling. We will see results for different hyperparameters tuning. Then we use on top of the cosine mean square error instead of binary cross entropy, which perform very well. So we have the mean square error loss function for the cosine prediction. Another option is to use concatenation. So we have the same biencoder. We have the same options to get an embedding for the text and the topic. So we have CLS, min and max pooling. Then we can take these two embeddings and concatenate them and have a separate layer, feed-forward layer on top of this concatenation with binary cross entropy loss on top of the concatenated input. Then we predict 0 or 1 binary cross entropy loss that if this topic is relevant to the text or not. So we use this concatenation and we added a more complex architecture on top of it. So instead of just concatenating U and V, which are the vectors that represent each part, we can do some transformation, like to concatenate the vectors, also concatenate the subtraction of the vectors, although the multiplication of the vectors. And we found this way we get better representation of both inputs and the combination between them. And also on top of it, we have the binary cross entropy loss, which predicts on top of these embeddings if we get 0, like this topic is not mentioned in the text, or 1, this topic is mentioned in the text. And also we have BERT, which is doing almost the same. So it's talking about the cosine similarity and also using a concatenation version. And we found out that also multiplication, not just subtraction, allow the model to perform better than just doing this kind of concatenation. So we saw different architectures. So we have basically the cross encoder, and we have a lot of architectures for the biencoder. And some important tips is that cross encoder mainly perform better than the biencoder because it learns the attention between because we have one BERT layer and we input the text and the topic together into a shared BERT layer. It learns the attention between each one of them. So it learns the attention mechanism between the topic and tokens in the text, which allows it to perform better. But the biencoder is faster. So if, for example, in inference time, we have T is the number of topics and we have N is the number of text, we can calculate in advance the embedding of the topics, and we don't need to multiply each time each text by a topic. So we just need to get the embedding of the topic separately, the text separately, and not have the multiplication input of the cross input of each one of them together, like to get a cross input of the text and the topics, and then we get embedding of this cross input. Also, we tried not just give the topic name like city trip, like to use the full description that describes this topic, right? Because we are using this kind of architecture that we have these two inputs, the text and the topic, we can allow ourselves to use a full description of the topic and use it to find the prediction. So we use it for very not clear topics like city trips. So what is actually a city trip? What we expect people to talk when they mention city trip. And we found also topic description is very valuable for this kind of model. Another tip that I want to share is about dynamic padding. So basically, most of the models, when you're using Hugging Face and most of the models, so you're doing max length padding. So you're fixing the batch length into 14, for example, and each batch will be at this length, even if the batch is shorter than that. So with dynamic padding, what we can do in the training is to set the padding to longest in the Hugging Face tokenizer, and even like to have the batch calculation on the longest length of the batch and not the whole corpus. And this training is multiply 5 faster. And also in inference, we can do even better, and we can sort the input. We can sort the different reviews by their length. Then we process first the shortest one, then we have the longest one at the end. That's how we make the batches to be at the same length, and then we don't spend time on calculating on the longest part of the batch. So we didn't do this trick on the training because we want the training to be random and not to be like to calculate the gradients or short reviews separately and long reviews. But in inference, we completely can do that, and that's why we sort the reviews. So how we collected the data for training? So first of all, some interesting fact is that we had some pre-collected data set with 40 topics. And we found out that if we train a zero-shot completely, like for example, a universal sentence encoder, which is completely zero-shot, we get some metrics, some performance. But if we increase the number of positive that we get per topic, we see with 100 examples of pairs of text and topic, we get this increase in performance. But from some step, let's say 200, we get a flat curve. So it's actually help us to define what is the amount of data we need to collect per topic in order to have a very good model. So let's say around 200 positive examples per topic is enough to train a good model. We don't need thousands of examples. So we did some smart partial labeling. We gave annotators a text and gave them just the top relevant topics that may be relevant for this text, not all of the. So we have 240 topics, so we didn't give each review all to tag all of the 240 topics, just the ones that are more relevant using zero-shot prediction for this text. Then we assign questions containing the related topics, and we add some random negative questions to have some randomness. So it looks like that. We know we have this text, and we just have this kind of topics because we know it's about, with zero-shot, for example, it's about romantic, but we had more topics from the same group of trip type to be included in the relevant categories to annotate if the topic exists in the text or not. But we are doing it for part of the labels and not all of the topics, not all the 240 topics. So this is how we are doing partial labeling, and at the end we get we insert to the model pairs, positive pairs and negative pairs. And here we have, for example, if the annotator click just on the romantic trip, so we will get a pair of the text and this topic with value label of 1, and all the rest with value of 0. Just the ones that are here, not all 240 topics. So we use we build dashboard for evaluation, confusion matrix, precision recall curve, also to see the separation between positive class and negative class, ROC curve. But mainly we focus on these metrics. So first we have average precision per class, which is the area under the curve of the precision recall curve per class. To get general metrics across all the labels, we use macro mean average precision, which is to take the average, unweighted average of the average precision across all the classes. We use weighted mean average precision, is to take the exactly the same but weighted with the number of positive examples that we have for each class. And we have the gap, which is the global average precision, micro mean average precision, which is to calculate the area under the curve of the precision recall for all of the classes together. We did a lot of hyperparameter tuning. As I mentioned, we have a lot of architecture. We have the cross encoder, we have the bi-encoder with the cosine, we have the bi-encoder with the concatenation. We have different sentence embedding. We have different concatenation method, and we see that some of the topics it's good to use description, some less. So this is like the best combination. So we want to use so the best combination was to use the bi-encoder concatenation with the CLS, and to use this concatenation method, and also to use description for some of the topics. So if we can see this result in terms of the map micro, map macro, mean average precision micro, macro and weighted. So basically the cross encoder was the best. You can see here, as I mentioned before, cross encoder because it learns the attention mechanism across the two of them together, because they are in the same input. We have better performance, but in terms of inference, it's very slow in comparison to bi-encoder. That's why we chose this option, which is we have less performance, but it's the best among the bi-encoder architecture. But we saw in production, we need to backfill and save the embeddings and the predictions for 240 million reviews, and we have a lot of reviews coming into booking every day. So we want to do a very fast inference, and this is why we chose this kind of model. Also, with the bi-encoder, we can get a text embedding because we have a separated BERT layer of the text and the topic. We can use the text embedding and save review embedding and use it for different tasks and different models in booking, not just for topic detection. So that's another reason why to choose a bi-encoder over a cross encoder. Some examples of results. So here you can see reviews and the topics that we detected. So very nice stuff. Thanks, Sophia, the reception. So staff and help support, reception topic, etc. And that's the example of zero shot. So zero shot is actually a topic that we didn't train on. So for example, allergy free room. And if we return the top reviews that mention this topic, we can see that it's actually found good ones. So should have some dog-free rooms for allergy sufferers. I got allergics, reacted the room, probably room dust. So it's actually talking about this topic, and also it's not exact match. Like it actually learns the semantic of that and how to retrieve the best reviews that are talking about this topic. Also, you can see for nature peaceful, peaceful and surrounded by nature, very calm and peaceful. So it's not exact match, but it's found a very good context of this topic. So when we taken this into production and when we serve some use cases, we want to define a threshold, right? So how we know this topic for sure exists in this review, because we get a probability as we saw before, and for some use cases we need to be able to decide if we want to show this topic or not. So for that we are using the F beta score criteria. So we define with the product if the use case is more precision oriented or recall oriented. Then if it's more recall oriented, we set a beta like equal to 2, like greater than 1. And then we calculate the F-score and then find the threshold that maximizes this F-score. If the use case is precision-oriented, so we use beta lower than 1, and then we get another F-score and use the threshold that maximizes this F-score. So this is how we pick thresholds. And in terms of serving it in real time and backfill it, so to save save storage space, we don't want to save all the 240 topics with probabilities for each review. So we just, with the threshold analysis, we drop 75% of the data, and we keep recall close to 1, and we save the most relevant, not most, but the topics that are really we have high chance that they are mentioned in the text, because we keep the recall close to 1. So we have a backfilling process, and we get all the reviews processing into our CAP, which is the content platform. We get all the reviews, and we using the model with GPUs and batch. We did some batch optimization about it. And we embedded 240 topics only once. We don't need to embed the topics each time in every prediction. So we just call, we take the embedding of the topic, we embed the new text that is coming, and we calculate the probability that this topic exists in the text. And we are doing this backfilling process every day. So every day we get new reviews coming into Booking. We process them with our pipelines, and we save the model predictions in Hadoop in our databases. So the main takeaways from this lecture is that we build supervised topic detection model using multiple data sources. We use question answering data source, we use reviews, we use forums, posts, etc. And we saw like how topic from one domain can help topic from another domain, and it's actually really nice. We saw different modeling options and BERT-wise architectures with zero-shot capabilities. We collected, we had a lot of data collection challenges, and we did a lot of optimizations. So let's see a quick demo. So for example, we can have this text, and we can press the get predictions and see what are the relevant topics that are mentioned in this text. So the hotel had everything. The room was super clean, modern, and had good facilities. Breakfast was very nice and staff helpful. The hotel had the best location. So we see it's mainly positive review. It's it mentions the food, the property cleanliness, the breakfast, room cleanliness, the location of the property, etc. Then if we want to explain or to highlight relevant words in the reviews that we see that are mention this topic. So for example, we have pet-friendly topic, and we know with some probability that the topic exists in the text. So with Lime and explanation in the demo tool, we can show which words lead for this prediction for this topic to be exist in the text. Also with attentions and everything like that. That's it. I will be happy to take some questions if you have, and hope you enjoyed it.
We have our first question. Are these models being evaluated in the language they were written, or are reviews translated to a common language first? Are there languages where there is not enough data to create good models or translations that impact the model results?
Sorry, I didn't get the questions again.
Sorry, let me try again. Are these models being evaluated in the language they were written in, or are the reviews translated to a common language first?
Yeah, so they were trained on the source language that they. So we use the multilingual BERT like as the pre-trained model, and then we fine-tune the multilingual BERT using the architecture I just showed you, and the actual text input is multilingual. Like it can be French, Italian, any language that came into the model, and we return the topics. Also trained on multilingual data set.
And the second part of the question was, are there languages where there is not enough data to create good models or translations that impact the model results?
So we trained the model on like all of the languages that we have in Booking. We didn't do an analysis per language to see the result. We did it just on top languages of Booking, like Italian, French, like more European languages. And so like we have good performance for all of them using it, because we're using as a backbone a multilingual model.
So the question is, how did you create the explanation shown in the last slide of the presentation?
Yeah, so here I'm using Lime, which is very well known package. So the idea of Lime is that you can insert the like it's an agnostic model, like you can give a Lime package a text, and then it will create variation of the text. So for example, I love that, and I love that hotel is dog friendly. Like it will try to create different variation of the text and like to delete some words. Then it will get prediction of the topic using different variation of the text. And then it learns which words affect most the prediction. So if we see that to delete the dog friendly, like reduce the prediction of the pet friendly by, I don't know, by 80%. So we know these words are very relevant for the predictions, and then this is how it's highlighted. Yeah, that's it.
The question is, the prediction probability is semantic similarity between topic and some description, correct?
Between topic and review. And we can replace the topic with description. So in the architecture I showed, like we have the text, which is the review, we have the topic, and we calculate the semantic like correlation, the semantic connection between these two. And we can replace the topic by a description, for example, as I showed for city trip, to have better semantic match. That's it. Great, thanks. Thank you so much.